Thank you, and good afternoon, everyone, and welcome to my talk. First, I'd like to thank Raul and Eric for inviting me to give a talk in the seminar. So, today I'll be presenting some work as part of my PhD at the Chair of Mathematics for Uncertainty Quantification in RWTH Aachen. And this project was also funded by the Helmholtz School for Data Science in Life, Earth, and Energy. And this work is about optimal power procurement for cellular wireless networks under uncertainty. And this is a nice collaboration with my PhD supervisor, Raul Tempona, and Nadir Ben Rachid from the University of Leeds. I'd also like to mention and thank Professor Alexander Mitsos from RWTH Aachen for his valuable inputs in the modeling section of this work. Right, so let's get started. So this is a brief overview of the structure of my talk today. First, I'd like to begin with a brief motivation of this work. So this work arises from the fact that worldwide mobile traffic is increasing at a rapid pace with the advent of new transmission technology like 4G, 5G, 6G, and so on. And more recently, as you might have noticed, 5G network coverage has increased by a very large percentage. And with increase in this coverage comes an increase in energy consumption of these transmission networks. And this trend is only going to keep increasing rapidly. A consequence of this high energy demand is increased greenhouse gas emissions. Currently, data transmission networks account for a significant proportion of all energy-related CO2 emissions. But around 80% of the energy consumed by cellular wireless networks still comes from fossil fuels. And this motivates the coupling of cellular wireless networks with renewable sources of energy to reduce both the costs as well as the carbon footprint of the telecommunications industry. And this has increased interest in research of so-called green wireless networks. So first, let me start with what is actually a cellular wireless network. So it is the infrastructure that allows all your mobile devices to connect to the internet and to make voice calls without any physical connection. And this infrastructure consists of multiple base stations, which each serve a small section of the entire network geographical area. Green cellular networks are not only powered by traditional power from the grid, but also by locally installed renewable power sources like wind turbines or solar cells. So now let us take a look at what happens inside a base station in detail. So each base station has a set of transmitters that transmit power that is received as a signal by your mobile devices. So each base station is also equipped with a battery to store the incoming renewable energy. And this battery allows the operator of the base station to control how much renewable power is used to power the transmitters, how much power to buy from the traditional grid to power the transmitters, PF, how much total power needs to be transmitted, this PTX, and how much extra power from the battery could be sold back to the grid, maybe for added revenue, PS. So these are the controls, the PF, PS, PA, and PTX. And the challenge generally is to identify these optimal controls for the operator to reduce operating costs and carbon footprint of the base station. So modeling these systems and basically modeling each component of the system and deriving an optimal power procurement policy for these base stations can be challenging, mainly due to two sources of uncertainty. Number one, uncertainty in the incoming renewable solar or wind power, and uncertainty in so-called wireless channels. I'd like to briefly go through a quick literature review on what has been done so far. So the solution method for this problem in literature can broadly be categorized into robust and stochastic optimization. So in the robust optimization approach, they construct a bounded uncertainty set, which includes all realizations of the stochastic variables, and optimizes only the worst case objective function value. While this approach ensures feasibility under worst case scenarios, this approach often leads to overly conservative policies. On the other hand, a stochastic optimization approach assumes a known probability distribution for all the stochastic variables and optimizes an expected value of the objective function over the joint PDF of the uncertain variables. Although this is a very natural interpretation of the stochasticity, this approach often can only be solved heuristically for very complex problems. Moreover, all the works that I've mentioned here have only considered this optimal control problem in a discrete time setting. So in our work, which has recently been published, so we propose a novel mathematical modeling as well as numerical solution framework that solves the optimal control problem for wireless networks with the following features. So we have a continuous time formulation for the problem. We have a finite time horizon, that is, we solve the optimal control problem only in the time span of 1 day. We have a multi-objective optimization subject to stochastic dynamics in the form of stochastic differential equations or SDEs. Also, optimization subject to some almost sure constraints arising from demand and capacity limits of energy systems and wireless channels, and subject to a quality of service probabilistic constraint at all points in time. So let us now look at what exactly each of these points mean and how we model the different components of the base station. And so that is the next section. So I will always keep this image of the schematic of the base station as reference. So first, and we basically are now looking to model each component of the base station. So first, let us look at the power balance of the transmitters. So the transmitters receive power both from the grid as well as from the local battery, PF plus PA, right? And this combined power is used to run the transmitters. And the demand of the transmitters comes from the total power that is transmitted to the users times some scaling factor, which accounts for transmission losses, plus some offset power, which is the minimal power required to keep the transmitter switched on. We approximate the total transmitted power by the number of users connected to the network times the power transmitted to the average user. Hence, the power demand of the base station depends on the number of users connected to the network at time t, which is denoted by this NU. One simple model that can be used, for example, is a simple sinusoidal curve given by this, which, for example, in literature has shown to approximate practical user patterns closely. For example, taking into account two peak hours, one from 9 to 10 a.m. and the second around 8 to 9 p.m. and low number of users at night, and so on. Next, we model the transmission system itself. The transmission system is subject to a lot of uncertainty that I briefly hinted upon before, and this is modeled with the help of what is called a wireless fading channel, which is denoted by psi as a stochastic process psi here. Let me explain this further. So imagine there is a transmitter at the center of a region given by this black dot here, and there is a distribution of users around the transmitter. Um, it is important to know that the power transmitted by the base station is not the same as the power that's going to be received by your mobile devices. The power received reduces as the distance from the base station increases, given by this term here, and is also subject to randomness via this multiplicative factor, which is the wireless fading channel denoted by psi, right? And this randomness is generally attributed to random interference due to moving objects in the environment, ambient noise, environmental conditions, and so on. The signal to noise ratio is one widely used quantity used to denote the quality of signal received by your mobile device, and it is defined as the power received by divided by some ambient noise in the logarithmic scale. And depending on this, a user is defined to be in outage, or a mobile device is defined to be in outage when the signal to noise ratio for that device is less than a certain threshold. One approximation we make here is that you can see that this is in the outage proportion over here is looks like some kind of an empirical average over a distribution of users. And in the limit of a high number of users, one can approximate this empirical average by an integral over a certain distribution of users, right? So this basically means that the transmitter now sees a distribution of users instead of individual users, right? So now, for the wireless network to offer a certain quality of service, the proportion of devices in outage needs to be less than a certain threshold with a very high probability, 1 minus epsilon over here, right? And this is the probabilistic constraint that the mobile operator must satisfy to offer a certain quality of service. Again, note that this is a probabilistic constraint at each that needs to be satisfied at each point in time. Next, how do we model this the wireless fading channel or the randomness and in continuous time? And for this, we use an SDE. We derived this SDE to model the so-called Nakagami fading channel or model, which has been shown to be a good data fit for cellular systems in urban and suburban areas. In this model, the instantaneous power is gamma distributed. It's a so-called Pearson type 2 distribution. And hence, we use a Pearson type diffusion to model the wireless channel. So this Pearson diffusion basically has a drift, which is mean reverting and linear in the state, and a squared diffusion, which is also linear in the state. Observe that the stochasticity here is not something that can be controlled, right? But what we can control, however, is the amount of power that you're going to transmit to the average user, this PTX. Under the constraint that the transmitter has a limit on the maximum power it can transmit. And the objective here is to maximize the expected revenue from having mobile devices connected to the network, which is given by equation 4. Next, we model the renewable power coming into the base station. And since this power is also subject to a lot of uncertainty, we model this using a stochastic process, capital R, that is actually the normalized instantaneous renewable power coming into the station. And to model the uncertainty in R in continuous time, we again use an SDE. However, we use a data-driven model here. And what do we mean by this? So our SDE is driven by publicly available forecasts for solar or wind power for the next day, which is denoted by this term P in the drift. So the drift here is designed such that the process reverts mean reverts to the given forecast data P. And the diffusion here is designed so that the process lies in 0 and 1 almost surely. And the parameters in the diffusion alpha and theta 0 are learned from historical discrepancies between the forecast and actual power production. What do I mean by this? So this calibration takes as input publicly available forecasts of the data of forecasts and the actual power production from the previous years, let's say 2023 here, and infers the parameters of the SDE based on the behavior of the error between the forecasts and real production. This procedure allows us to then produce confidence intervals for the real production for a given forecast in the future. The renewable power into the base station, or the instantaneous power into the base station, is then just a normalizing factor times this R. Next, we want to model the battery in the base station. And for this, we define the charge in the battery A, capital A, as the state variable. Here, one can control PA, the amount of battery power supplied to the transmitters, and PS, the amount of power sold back to the grid for profit. We use a simple ODE model for the battery, where you have just the rate of change of charge in the battery is equal to the incoming power. What makes the model interesting is the so-called characteristic curve of the battery, and this tells us how much power the battery can charge or discharge, depending on how much charge is present in the battery. For example, when there is no charge in the battery, it cannot discharge any power, and it tries to store charge as fast as possible. On the other hand, if the battery is fully charged, it cannot store more charge, and the battery can discharge as fast as possible. Here, one tries to maximize the expected revenue obtained from selling the extra power from the battery back to the grid. The power is generally sold at the spot price of electricity, for which data is publicly available in a 1 hour frequency, for example, like this. Finally, we look at the model for power from the traditional grid. Recall that the operator can control PF, which is the power bought from the grid. And this power is also bought at the spot price of electricity, KB. And the operator aims to minimize the expected financial cost of buying power from the grid. Furthermore, in order to encourage the cellular network to use more renewables, we impose an additional penalty on buying power from the grid. This environmental penalty is quadratic on the grid power bought and prevents the operator from buying excessive grid power to power the transmitters. And the operator also needs to ensure he minimizes this expected environmental penalty. The last thing is that although this work formulates the optimal control problem for a 1-day operation cycle, this could lead to impractical, spurious results at the end of the day. For example, any optimal policy that would minimize costs would likely ask the operator to sell all the stored energy in the battery at the end of the day to generate revenue. And to avoid such impractical policies, we develop what we call a running horizon framework. And this involves two facets. One is we add a fictitious or fictional revenue from having stored battery charge at the end of the day. And the idea is to maximize this revenue, this expected revenue, right? So this encourages the operator to store energy at the end of the day. Number two is we extend the horizon from 1 day to 2 days, but we only apply the optimal policy for the first day alone, right? So this means that the optimal policy is updated daily, but we would require 2-day ahead forecasts of all the required inputs. That is the renewable power forecast, energy price forecasts, and the mobile user profile. Okay, so putting all these elements together in a base station So the optimal control problem for our base station can be formulated. So let us now list down the components required to formulate a standard stochastic optimal control problem. So first we start with defining the finite time horizon, which is from 0 to capital T, where 0 represents the start of the current day and capital T denotes the end of the next day. So 2-day running horizon. Next, we have the control state process, which we denote by this bold capital X, which has three components. One is A, the amount of charge in the battery, capital R, the instantaneous renewable power normalized, and psi, which is the wireless fading channel. And we have seen that it evolves according to the SDE dynamics that we have seen before. One can see that the drift terms here are coupled, and the control appears only in the drift of the battery dynamics. And the diffusion terms are all uncoupled and are uncontrolled. We can group these dynamics together and write them as one multidimensional SDE with a drift vector capital F and diffusion matrix G, where only the drift is controlled by a control process capital Phi here. So what is the control process? The control process is the set of four controls that we have seen before, right? PA, the power from the battery to the transmitters, power bought from the grid, PF, power sold back to the grid, PS, and power transmitted to the users, PTX, right? In this work, we consider the control process to be an adapted Markov process, which means that the control process, capital Phi, is a function small phi of the current time and current state, x at time t. And this function phi is called the Markov control function or policy. Next, we define the set of admissible controls. In this problem, we need to ensure that the control process respects the various demand and capacity constraints of the system at all points in time. And these are listed down again here. So this is the power balance of the transmitters. This is the characteristics of the battery. You have the maximum power transmission limit, and you have some non-negativity constraints on the controls, right? So for a given state X at current time T, we denote by this bibliographic A at time T and state XT, the set of controls that satisfy these constraints given time T and the state. Subsequently, we denote by this calligraphic A the set of all admissible policies that satisfy these constraints for all times, for all points in time, and for all realizations of the stochastic process X. Finally, we define the cost function. So remember, the base station operator in a green cellular network must minimize both financial costs as well as the so-called environmental penalty. And to deal with this multi-objective optimization, we introduce a parameter W to balance these objectives. So we define the net utility cost, calligraphic U, as the weighted sum with W of the two costs, the financial cost and the environmental penalty. And the objective would be to minimize this whole utility cost, we call it. So now let us recall what the individual financial costs and environmental costs are. So we have C1, which is we have the financial costs, which are C1, the financial cost of buying power from the grid, R1, which is the financial revenue from serving customers connected to the network, R2, which is the financial revenue from selling energy back to the grid, R3 is the fictional revenue from having stored battery charge at the end of the day, and C2 is the environmental penalty of buying grid power. If we write this down explicitly, it looks something like this, where we can see that we can split the cost into some running cost times plus a terminal cost. And we group all the running cost terms under the function A and the terminal cost under the function B, right? And with this, we can define a so-called value function, which describes the value of the minimum possible cost of the system, given that at time t, the process capital X has a value small x. And this is given as the minimum of a certain cost over all admissible policies belonging to the set calligraphic A. So where this cost functional j, t comma x of phi denotes the system cost, given that the state capital X has the value small x at time t, and given that we follow the policy phi. And the goal of the optimal control problem now is to characterize the value function, which we denote by u, and find a policy phi star belonging to the set of admissible policies that attains the minimum cost. All right, so now collecting all these components of the optimal control problem, we can finally pose the primal problem as follows, where we want to find the policy that minimizes the following cost over an admissible set of controls calligraphic A, given the system dynamics SDE. And remember, we still need to satisfy the following probabilistic quality of service constraint at all points in time, as we have seen before. For convenience, we can now write down this outage proportion function as a function of the state and the control. And we can also re-express the probability as the expectation of an indicator function, right? Unfortunately, one cannot solve this primal problem in the standard way using dynamic programming. And this is because this probabilistic constraint here controls the joint PDF of the current state and controls. On the other hand, in standard dynamic programming, the optimal policy is generally a function of the current state and time alone, and not a function of the current distribution, right? So hence we cannot apply standard dynamic programming. So the key idea here is to relax the probabilistic constraint in continuous time using the well-known Lagrangian relaxation technique. And this gives rise to the so-called relaxed problem. So now the so-called Lagrangian is the original cost plus the Lagrange multiplier times the violation in the probabilistic constraint. Note that now the Lagrange multiplier is a function in time, since we need to satisfy the constraint at all points in time. Now, the objective of the relaxed problem is to minimize the Lagrangian over all overall policies in the same admissible set we have seen before, and given the same dynamics that we have seen before. We can then rewrite this Lagrangian as to group together basically the running cost plus the terminal cost, right? Yeah, and this new running cost we denote by A lambda. Now, this relaxed problem is in the form of a standard optimal control problem, which can be solved by dynamic programming. But we still need to get the optimal Lagrange multiplier function lambda. And for this, we solve the associated dual problem. So what is this problem? We need to determine the optimal lambda that maximizes the dual function we denote by theta. So the dual function theta evaluated for a given lambda is basically the Lagrangian evaluated at the optimal controls for that given lambda, right? So next we will see how we solve the dual problem and get the optimal controls. So first question is, how do we evaluate the dual function for a given Lagrange multiplier function lambda? So each evaluation of the dual function basically means solving the relaxed problem for the given lambda to get the optimal controls phi star. And since the relaxed problem is a standard optimal control problem, we can apply the classical dynamic programming principle and derive the associated nonlinear Hamilton Jacobi Bellman PDE, right? And this looks like something like this equation, basically. Um, and the PDE solves for the value function that we introduced earlier associated with the relaxed problem, with the final time condition coming from the terminal cost of the system. This term, calligraphic H over here, is the so-called Hamiltonian, which is defined as follows, which would be, it is the pointwise minimum over the controls phi of this term over here. And the nonlinearity comes from the fact that the optimal phi, or like optimal pointwise phi, will be a nonlinear function of the gradient of u. Right? In this work, we solve this PDE numerically using an upwind finite difference scheme. Um, this is a first order in time and space scheme with the numerical update rule given as follows. It's a bit complicated, but basically the idea is that you can see that the value function at time step n-1 can be written explicitly as a nonlinear function of the value function at time step n. Okay. So now the next challenge is that now the Lagrange multiplier, uh, remember, is now a function in time. And hence, the dual maximization problem is an infinite dimensional problem, right? You're maximizing over some functions. Now, to solve this practically, however, we approximate the Lagrange multiplier by a piecewise constant function. And this corresponds to satisfying the probabilistic constraint, not at all points in time, but on average over a finite number of subintervals. Effectively, this approximation leads to a maximization of the dual function over an L-dimensional vector epsilon, where L is the number of piecewise constants in the Lagrange multiplier. And this epsilon is what I call the amplitude vector of the piecewise constant function. And for this approximation, one can prove that this dual problem is convex, non-smooth, and L-dimensional. The finite dimensional approximation of the dual problem is now given as follows, where lambda L denotes the piecewise constant approximation of the Lagrange multiplier with L piecewise functions, or sorry, L piecewise constants. And the corresponding Lagrangian is written as follows, where you have the original costs plus a summation over each interval of the respective amplitudes times the violation in the or the average of the violation of the probabilistic constraint over the finite subintervals in time. And this term here is commonly known as a subgradient in dual optimization, and we shall see shortly why. For this, we first see how we can numerically solve this convex non-smooth dual optimization problem. For this, I'd like to briefly introduce the concept of a subgradient. So a subgradient can be thought of as an extension of a derivative for non-smooth functions. For a concave function, for example, the subgradient at a point is defined as a set of slopes for which a line passing through that point lies completely above the function. Right? So at the differentiable points of that function, the subgradient then collapses to a single value, which is its derivative at that point. And using this, one can define the conditions for a non-smooth concave function to attain its maximum, where this theorem, which is given by this theorem, and this theorem says that the function attains a global maximum, or a concave non-smooth function attains a global maximum value if and only if the zero vector is an element of its subgradient. And we use this fact to build what is called a subgradient method to solve the optimization problem. You can think of the subgradient method as an extension of the gradient descent method for non-smooth problems. So the subgradient method follows this update rule. This looks very similar to the update rule for a gradient descent, right? Where you have the k plus 1th iterate being equal to the kth iterate plus some step size times any subgradient of the dual function evaluated at the kth iterate, right? The main change here, however, is that this is not going to be a descent method, and one would need to keep track of the best or the highest dual function value among all the iterates so far. Also, one would need to compute a subgradient at each point. For our dual problem, as we have seen before, the subgradient is just the average violation in the probabilistic constraint over the finite subintervals that correspond to the piecewise constant Lagrange multiplier. How do we now compute this expectation? Um, for this, remember that we have solved the Hamilton Jacobi Bellman PDE for a given lambda. So what we do is we store all the value function and its derivative values on a numerical grid in a lookup table. Then we run optimal paths of the control state process X, capital X, forward in time, where the corresponding optimal controls are going to be computed using the stored values in the lookup table of the value function and its derivatives via interpolation. We then estimate this expectation using a Monte Carlo average over MSG sample paths. Of course, we also need some discretization to numerically estimate this integral over here. Since Monte Carlo estimates also have a statistical error, we only have noisy estimates of the subgradient, and hence our method is a stochastic subgradient method. This image depicts the proposed dual optimization algorithm. So remember that we still have to find out a good refinement of the Lagrange multiplier L. So for a given L, we of course run the stochastic subgradient method for a given Lagrange multiplier refinement L until convergence. But we also, on top of that, keep refining our L until a certain required tolerance is met. And in our algorithm, as you can see, the convergence criterion is the subgradient norm. That is, the algorithm stops once the norm of the subgradient is below a certain relative tolerance. Now, for quick convergence of the stochastic subgradient method, it is crucial to choose a good initial point. And for this, we develop a heuristic kind of, we first develop a heuristic kind of an algorithm which searches basically for a good starting point for the level L equal to 1. No, remember that L equal to 1 corresponds to the Lagrange multiplier just being a constant function in time. So the algorithm basically starts with an arbitrary value for lambda, then basically keeps increasing it by a factor beta f here until the subgradient changes sign or its norm attains a rough initial relative tolerance. Now, to further enhance this heuristic algorithm, we use the output of this algorithm as an input for what is called the limited memory bundle method, or LMBM, which is an advanced technique for deterministic non-smooth optimization, which requires deterministic function and deterministic subgradient evaluations. Even though we only have stochastic subgradient evaluations, the key idea here is that we use LMBM in a regime far away from the optimal points, where changes in the dual function values far outweigh the noise in the subgradient estimates. And we do this only for the refinement level L equal to 1. For all subsequent refinement levels, we use the optimal lambda at the previous refinement level as a starting point for the optimization at the current level. All right, so now in the last 10-15 minutes, let us look at or let us visualize the results of applying the above numerical procedure to the optimal power procurement problem for cellular networks, right? First, we set the parameters phi threshold to 10 power minus 3 and this epsilon to 0.1, which basically means that we need to solve this optimal control problem under the constraint that the outage proportion should be less than 10 power minus 3 with a probability of 90%. That is 1 minus zero point 0.1. Okay. So first, let us look at how the value function solution or the solution to the Hamilton Jacobi Bellman PDE looks like for the obtained optimal Lagrange multiplier. So here we visualize the slices of the function on the axis of time and one state variable while keeping the other state variables 0. So we do this for all the three different state variables that we have, right? So to get more meaningful results, let us now visualize the performance of the dual optimization algorithm itself. So we first look at the optimal dual cost obtained, which is this negative 660 euros, let's say, in these units. All right, so this as such maybe does not, in the absolute sense, does not have any meaning, but what we do is we compare these costs to two associated optimal control problems. One is the same optimal control problem, but instead of this probabilistic constraint here, we want to satisfy this constraint almost surely, right? And the second one is the second optimal control problem is we remove this constraint completely, right? So we can deduce that the optimal cost for the chance constraint problem must lie between the optimal costs of these two problems. More specifically, the almost sure constraint problem must lead to a higher optimal cost, and the unconstrained problem must result in a lower optimal cost. This is exactly what is confirmed by our numerics. We also see that the chance constraint problem leads to a optimal cost that is much closer to the cost of the unconstrained problem and much lower as compared to the almost sure constraint problem, which kind of motivates why we use probabilistic constraints here, even with high confidence when compared to almost sure constraint problems. Also, one can see that the dual cost, um, yeah, after the initialization procedure is also pretty close to the actual optimal cost, meaning that the initialization procedure itself gives a good initial point for the subgradient method, which means that we do not require too many iterations to get to the optimal from a well-chosen starting point. So apart from the dual costs, let us now see how the subgradients behave at each, or the subgradient norms behave at each stage of the algorithm. So first we see how the subgradient decreases with each iteration of the initialization algorithm, right, and reaches the required initial tolerance in 3 steps. Next, we see how the subgradients behave at each stage of the subgradient method, which each iteration of the subgradient method for a fixed L. We see an oscillating behavior in the first 10 iterations. This is because in our implementation, we used a constant step size for the first 10 iterations before then reverting to a diminishing step size. And this choice was made to speed up convergence. We also see that the norms at each refinement level L have reached the required tolerance, meaning the stochastic subgradient method converges to the required tolerance in the subgradient norms for each level L. Next, we see how the optimal Lagrange multiplier evolves as we increase the refinement from 2, which is the blue line here, to 4, which is the red one here, and 8, which is the yellow one here. And the algorithm stops at L equal to 8 as it has and does not refine it any further because it has reached the required subgradient norm tolerance already. So now let us actually see what the optimal power procurement policy looks like. And these are the important outputs of the algorithm that the mobile operators would actually receive from our algorithm. So first, we get the expected power demand for the base station for the next 24 hours, along with confidence intervals. Right? So this is number one. Number two, they see how much expected green power from the battery would be used to supply the transmitters in the next 24 hours. Number three, how much power the operators would need to buy in the next 24 hours, everything with confidence intervals. Next, how much power needs to be sold in the next 24 hours, in this case, not much. And next, how much charge needs to be stored in the battery for the next 24 hours. Right? So these are the practical outputs that the operator is going to get from the algorithm. Next, we would like to see if the obtained optimal policy actually not only reduces costs, but also satisfies the probabilistic constraint that we have. For this, I'd like to show you first how it would look if we solve the unconstrained problem. That is when we remove the probabilistic constraint at all and solve the optimal control problem. And you see that in this case, the outage proportion is always above the threshold at all times, meaning this probability is 1. And this is 1 minus epsilon. Um, and meaning the solution to the unconstrained problem basically only reduces costs without regarding quality of service. However, the optimal solution for our chance constraint problem, or that given by our algorithm, ensures that the violation in the probabilistic constraint is 0, at least in an average sense, if not at each point in time. Okay. Last, to verify the robustness of our algorithm, we also investigate its performance under various scenarios, both specific and random. So first, we look at 5 specific scenarios that could be of interest to mobile operators. So first, in the first scenario, we see if what happens when there's no renewable power for a day. Scenario B, what if the wireless fading channel suddenly becomes low? Scenario C, when there's high weight assigned to minimizing costs and the environmental penalty is neglected. Scenario D, when the revenue from serving users reduces. And scenario E, where we want to satisfy the probabilistic constraint with a much lower confidence than 90%. Right? So what we do is we run the algorithm for each scenario, we obtain the optimal power procurement policy, and basically integrate the area below the average power curve that to give the average energy that needs to be procured in the next 24 hours. And we compare these quantities for each of these scenarios to see how the optimal procurement policy behaves. So, for example, in scenario A, when there is no renewable power for the day, the operator would need to buy more grid power when compared to the base scenario. Or, for example, in scenario C, when the financial costs are given very high weightage and no weightage is given to the environmental penalty, large amounts of the stored battery energy are going to be sold to the grid for revenue. Another interesting scenario is the scenario E, where we decrease the confidence level of satisfying the quality of service constraint, right, from 90 to 80%. Here you see that low amounts of power are provided to the transmitters, meaning that the operators choose not to provide too much signal in order to save costs. Lastly, we ran 50 independent runs with randomized model and algorithmic parameters to check the robustness of our algorithm. And we see that in all 50 runs, the algorithm provides an optimal policy that satisfies the optimality in the subgradient norm up to the prescribed relative tolerance. All right, so finally, the key takeaways from the talk. So first, we provide a novel mathematical formulation of a short term continuous time optimal control problem for wireless networks under uncertainty and chance constraints. Number two, we deal with the time pointwise chance constraint with a novel Lagrangian relaxation in continuous time. Uh, Number three, we develop a robust numerical procedure that involves one, a finite dimensional approximation of the Lagrange multiplier. Number two, an upwind finite difference scheme to solve the HJB PDE. Number three, a stochastic subgradient method to solve the convex non-smooth dual maximization problem. And number four, an LMBM boosted initialization procedure to get a good starting value for the subgradient method. One key takeaway from the modeling part is that you saw that replacing an almost sure constraint by a chance constraint with high confidence for an optimal control problem reduces costs significantly for cellular networks. And the various numerical experiments that we conducted kind of highlight the practicality of the proposed approach, which could maybe make it useful as a decision-making tool in the telecommunications industry. I believe that this project is just the start of an exciting research line where some of the research directions are as follows. So one could, of course, include more stochasticity in the model, for example, including stochastic energy prices, user traffic profiles, and so on, which basically means more running dynamics, right? A higher dimensional state process, and hence a higher dimensional Hamilton Jacobi Bellman PDE. One might think that finite difference schemes for this PDE might become too expensive, so maybe we need to think of other ways to solve it. Number two is to handle extremely rare probabilistic constraints, where you want to satisfy the constraint, the quality of service constraint, with a very high probability, like 99.999%, which are actually practically relevant for cellular wireless networks. One idea for this is to use importance sampling for the subgradient estimation here. Another idea is to maybe adaptively refine the Lagrange multiplier function lambda, right? So in our case, in our work, we set the piecewise constant function lambda in like uniform subintervals in time. Maybe that is not the optimal way to go about it. We can do something more clever. So I'd like to end the talk with the paper that this talk is based on. You will find many more details in the manuscript. Please have a look if you're interested. And with that, I'd like to thank you all for your attention, and I'd be happy to answer any questions.